Well, this is the video podcast for Chapter 14 on flood hydrology, and we've already talked about floods from an urban perspective, but floods are really part of something much larger, what we call the natural flow regime, and floods are an important part of many aspects of the ecology. And so it's important to learn in this class more about what are the different kinds of floods that are out there and how do floods fit within the overall hydrological context. So I'm going to break this into two video podcasts. This first one is going to present to you types of floods with definitions and examples. And then the second video podcast is going to address this overall concept that was formalized in 1997 called the natural flow regime. Okay, well, from the most basic sense, flood is simply water that rises to overflow land that is not normally submerged. Pretty simple. I'm sure you're familiar with that concept. And we can define a river flood specifically with regard to a channel. And I've shown you this diagram before. You can see that there is a well-defined geometric cut into the land. We call that a channel. And anytime that the flow is too large to be contained within the natural channel network, then that you get the first part, which is water spilling out of that. This is a nice classification system that just illustrates the different kinds of things that can generate river floods or estuarine and coastal floods. We're not going to talk about the estuarine and coastal side, but just looking at the river flood side, there are factors that are along the bottom that I've indicated in red determine whether water is going to overflow the channel or not. And then on the top, what are the things that are actually generating the water? And then those two come together and make the floods. And in this case, talking about river floods. And I also am going to break these into two. When the water comes from instantaneous effects like landslides, dam failures, or possibly even ice jam as an instantaneous effect, like a dam break kind of effect, versus rainfall that induce runoff. And when you have an excessive amount of rainfall compared to basin storage capacity, then you can get a flood. Let me just illustrate the case of an instantaneous flood using the second largest loss of life event in California history, and that was the St. Francis Dam failure on March 12th of 1928. St. Francis Dam was one of the large works that was very prominent in its day. It's a concrete arch dam, and you can see it in the photo here, and then on the right is a picture of the dam after it had failed. At the peak of this event with dam failure, there was about 1.7 million cubic feet per second. And if you haven't heard about this before, you can go on the internet, and there's a lot of great historical information that talks about it. But what you can imagine is when you have a failure like this, that's fairly instantaneous, not perfectly, but you get a giant flood wave that is then going to create a lot of damage. And in this case, the main culprit here wasn't the structure of the dam itself. It was geological considerations in the hillside. At least that's what investigators have come to the conclusion of after the event. And specifically, there's a lot of weaker materials with the east side, which is shown on the right here. That east side had a lot of old landslide debris and what are called schists, which are rocks that can be easier to be impacted by water. And so that landsliding debris was thought here, according to this one investigator, Grunsky, that probably failed in some way associated with water and possibly additional landsliding that occurred, or just simply uplifting and shifting and not being able to bear the weight of all the water held behind the dam. In addition to the main flood wave, there was a secondary flood wave. It was actually the west side of this structure that was first kind of at risk because it was, there's a lot of fractures in the rock that was under that side, and so water was leaking already, but it wasn't considered catastrophic. But once the east side broke, then the reconstruction is that then the west side collapsed as well. And this is a view of the valley downstream, and what you can see here is the whitish color that is the active area of inundation, which actually comes all the way up to here, and just the carnage that took place. And it was even worse as this happened in the middle of the night when about 600 people were, sleeping and, not in a position to escape. So obviously that kind of event, instantaneous, that's a flood, and, very, very important to understand, but a very unique kind of hydrology and response compared to the other kinds of river floods that we're going to look at. And that all falls into this category of rainfall runoff floods. And what I've done is I've come up with my own little classification of different kinds of floods. This isn't something you'll find in the literature, but it's something that I've made up that helps me think about the different kinds of events and their hydrological context. So a river flood is something that's going to occur because an excess of rainfall relative to watershed storage capacity. And this is just an example of the spatial distribution of rainfall, with the reds and purples being high values and blue being low. And you can see this band of rainfall, and you can see this high concentration, high intensity that can take place. And I'm not going to read these names, but you can see them, and we'll work through that over the next few slides. I also want to go back and remind you, the next two slides here are actually from Chapter 4, and they remind you of these two different kinds of runoff, Hortonian overland flow and saturation excess overland flow. So recall that in HOF, the intensity is faster than the ground can absorb, and so runoff occurs regardless of what the subsurface conditions are otherwise. And this is what many of you I know think about, that if you increase the slope, you increase runoff, and that is thinking like Hortonian overland flow. However, it's much more common to have saturation excess overland flow, or just saturation overland flow. And what happens here is that you have soil, and eventually you've filled the storage capacity of the soil, and then you have runoff. And what matters here is that the occurrence of this filling to capacity of soil is highly variable over the landscape. Like if you look at the water table adjacent to the channel, the height above the water table to the ground surface is pretty small, forgetting the litter layer that's shown here. On the other hand, at the top of a hill, that space is quite high. And even if you have shallow bedrock, even if the space isn't much different between the low and the high areas, there's still the fact that high areas are dispersing water away from them, what we call divergent flow, and as a result of that, water is dissipated away over a larger area. On the other hand, the lowlands tend to be areas that are convergent, and that's something that you can see if you look at contour lines on a map. It's a little bit beyond the concepts for this class, but it just gives you another reinforcement. And I also want to remind you that the speed at which water flows through the subsurface is proportional to the slope. It's the slope of the gradient driving water, but that's also going to be proportional to the land slope as well in most cases. And so as a result of that, subsurface flow will increase with increasing slope. So if you're designing an infiltration strip or a green roof or something like that, you have to account for the subsurface flow rate, not just like a Hortonian overland flow rate. Okay, so that's a big reminder of what you should already know, but it's really, really important, and so I want to emphasize it, because now we want to get back to the topic of floods. And this is the really cool thing. There's this idea that was developed called the variable source area concept. And the idea here is that the majority of runoff, and inevitably the area that's contributing to floods, but the majority of runoff exiting a basin is driven by a small portion of its area. So how does this work? Well, here's a map of a watershed, and it's shown 4 times. So let's start at step 1. I've made a little 1 here for you. And what you can see is this squiggly line is a channel network that's present when the condition is dry. So when channels are dry, the location of a head of a channel where there's actually flow taking place might be at these 2 locations that I'm pointing to with the arrow. When rain begins, as rain is occurring, the first place to saturate, other than the fact that the channel is already wet, is the head just upstream of the head of the channel. These tend to be areas that are what we might call hollows, or places where flow is converging, like in somewhat like a bowl shape. And so you have excess water compared to what the soils can hold, and it spills out. And what happens over time with storms is that more of these hollows become fully saturated, and channels then extend up through them. And you can see that now the channel network is much greater. What's happening is it's not actually cutting channels, not like physically cutting. These physical channels already existed. They were just dry, but they existed in hollows where there's a higher tendency for early saturation. And so, and in some cases there may not be. I mean, there may just be flat areas where you have then sheet wash flowing over that. And so as the storm goes on, we see a greater and greater extension of channels and greater saturation of a basin. So at the onset of runoff, maybe only 5% of the watershed is actually contributing runoff into the channel. That's not to say that there isn't dynamic flow and groundwater flow everywhere, but in terms of the surface expression of runoff in streams, only a small area is contributing to that. After a while, about 20 to 25% of the basin will be contributing to the flow that you see at the outlet. So this is the variable source area concept, and it's very important, so I encourage you to study that. Well, when we look at rainfall-driven floods, of course, rainfall is going to be an important factor to determine what happens. And here's a plot that shows the drainage area on the x-axis and the peak discharge that's been generated from drainage areas on the y-axis. Unfortunately, a lot of the little dots are hard to see, so I've provided you with some envelope cloudbursts. And the line here represents a fit to these maximum values, but not necessarily trying to say that has to be the maximum value. And the types of events are quite different. So very small areas have the largest peak discharges during cloudbursts. So remember, well, I don't know if we haven't talked about it yet, but cloudbursts, let's see, do I have a, yeah. We'll start there. So cloudburst flash floods, this is where essentially you do get Hortonian overland flow. Like rainfall rate so vastly exceeds infiltration rate, and the rain is focused on such a small area that we quickly run off and then fill channels beyond capacity. And here are some maps. These are contour maps, and the contours here are in rainfall amounts. And then you can look at the time, like 2030 on July 15th, 2003, and it goes like 20, 23, 2, and then 5. And you can see how there are these very dense areas of intense precipitation. In other contexts, I've called this like a Charlie Brown kind of flood, because it's like a little, one cloud kind of moving across and raining on your parade. So that they can produce very intense floods in really small drainage areas, but they don't work for large areas. And the reason for that is that even if one part of a watershed is getting hammered really hard, the fact that the rest of the watershed might be quite dry means that by the time you aggregate all that together in a downstream channel, you might have transmission losses or just not adding up as much. So the fact that in general, watersheds, as you move downstream, that you have a decrease in slope and you have a much larger contributing area, those factors work towards decreasing the amount of stream flow. Okay, so at the higher end, for large drainage basins, we're going to have hurricanes or large-scale regional systems like nor'easters, or just long-lasting, large regional storms. Here's some screenshots to show you what you might see in a flash flood. So this photo on the left, you have a dry channel bed, and here is a flood, a flash flood, like the very head of it, as it's about to roar down this channel. So that's, if you were here in this dry channel, you might have no rain on you at all, then from one moment to the next, this massive flood comes roaring down the river like a wall of water. Okay, now another type of rain on snow event, another type of flood is a rain on snow event. Now, the idea of this is starting to change, and this is especially in a California context. A rain on snow event in general is when you have warm rainwater for a sizable storm that falls on a snowpack in the mountains. And if you compare the discharge associated with just a regular rain event in the mountain versus when rain is on top of snow, for any given return period of event, you get a significantly larger amount of discharge that's happening. This is per unit hectare of land. So that means each unit of land produces disproportionately more water because that water is coming from the snow. So the rain is unlocking previously stored water that's in the snowpack. Now, as I was saying, some of the thinking has changed because now we recognize, especially in California, that a lot of rain and snow events are associated with what we call atmospheric rivers. So an atmospheric river is when a storm is coming across the Pacific Ocean in a very narrow band, and typically it's coming from a tropical region where it's quite warm. And then that band will stretch off a narrow width of California and create a relatively intense storm. So it's almost like a blend between a cloudburst event, that may last for only 1 or 2 days, but it's very warm, and so raining on top of snow in January, that will have a disproportionately large effect. It's not always true that these would be atmospheric rivers, but we're learning more and more that there is this idea of disproportionately fast flowing, storms that are coming into California from the tropical Pacific. So when you have a snowpack, and it's crudely shown here from this diagram, the gray area here is a dry snowpack. And as you go to the front, you transition from a snowpack where it's raining on that, and snow, like soil, has a capacity to hold water. So it's going to be holding that. But then in the front edge down here, there's going to be a discharging zone where we have an excess of water and it can't hold it. So both between the melting water and the water that's raining on it, then there's a discharging zone. And the Corps of Engineers has come up with this simple diagram. It's one of these three-dimensional diagrams, like I've shown you some of these before. So you start on the x-axis and you say, how much rainfall am I having? It's like precipitation is rainfall in inches. And then you say, well, what is the temperature of the rain? And so for a given 7 inches of rain with a temperature of 40 degrees Celsius, then you can expect some, 0.4 inches of melt. But for the same rainfall, if that rain temperature is, 80 degrees Fahrenheit, this was 40 degrees Fahrenheit, now you go up to 80 degrees Fahrenheit, and now you get, 2.3, 2.4 inches of melt. So that's a significant difference depending on, doubling the temperature of the rain. And you can see from the equation here, it's just a linear function. So these are all lines and the effect is a linear one. But, if you took this function, you could actually create a three-dimensional plot if you like. The next type of river flood, rainfall-induced river flood, is a channel overspilling flood. Well, this is pretty much what you imagine it to be. You have more water from rainfall, you've exceeded the capacity of the soils, and so now you have runoff. You may have that variable source area thing going on. And so you take a channel network such as that shown here, and you can see where these tributaries are coming together. And then here's the same area zoomed in, and you can see dramatically wider confluence. And then look at how this is all flooding over. So the channel capacity is full. It spills out, and it will then move laterally across everything of that elevation, and then it can continue to fill up. One of the things I hear lay people talk about, with a flood is like, I don't have to worry about it, I'm 7 miles away. Well, flooding is not a function of distance, it's a function of elevation. So as the water floods up, it's going to be spilling and moving away. And I mean, of course, you have to have volume, but if you're at the same elevation as adjacent to the channel, it's going to get you, and then it's going to fill up according to that elevation. So that's something that's important to keep in mind. When we look at channel overspilling event, the one that really sticks out from my mind is the 1993 flood in the Mississippi River Valley that I was just showing you. And what this shows, just to put it into context, is an analysis of the flood history of the Midwest from 1941 to 1969. And you can see that each one of these plots is a different month, so January, February, March, and so on. during that period. And then the y-axis is the number of floods that took place. You can see floods can occur in every month, but the months of March, April, May, and June, possibly even July a little bit, but those have the most floods consistently over this 28-year period compared to the other times of the year. So if we look at what happened in 1993 that led up to the flood of the Mississippi River, you can see that it wasn't one event. Like everything I've talked about before is very event scale, like this variable source area concept at an individual event. But what you can see here is starting in July 1992, so a full year before the flood, there was an excess observed water, the white bar, compared to the average over the long term. And there were a few months like August and October where there wasn't, but for the most part, you look at July, September, November, December, January, April, May, June, July, August, all of those months had excess water. And even in the months where it wasn't in excess, it's pretty close, so it's not like the system ever got a chance to dry out. Just like a large amount of rain steadily over a year, and then look at the differentials here, like greater than 4 inches of precipitation taking place in each of these months. So the flood stage, so here, this shows July and August, so July 1, 1993, and then the beginning of August 1993, and the river stage in feet. So 30, it's starting at 30, but obviously the flood stage, the stage could be lower. And above 30, that's flood stage. The previous record from 1973 was 43.2 feet, and the peak on August 1st was almost 50 feet. So, very large flood that had huge consequences for the Midwest, and there have been a lot of changes in, urban development and flood policy since then. Now, the next one is a type of flood that you may not be aware of. I call it the rainfall ponding flood. The closest thing I could link this to for you already would be the kinds of hydrology associated with mineral flat wetlands that we talked about in the wetland lecture. But the idea here is that you have an impervious surface or one that is pervious but has a very shallow water table, and you have a large lowland area. And when I mean large, it can be quite large. As I'll show you in examples in a minute. And so the water simply ponds over this large flat surface, and it has nowhere to go. It's just, basically it just ponds up. Whatever channel there might be could be separated by a levee. If it's a managed system, it could be separated by weirs or flap gapes, one-way valves of some kind that prevent the water from getting out. It also could be that the channels are already full. Like even if they haven't flooded, they're pretty much approaching capacity, and so again, there's nowhere for water to go. So this isn't a case of water filling the channel and spilling out on the floodplain. It's a case of the floodplain already being full by the time the channel is full, and therefore it's almost like a reverse flood if you want to think about it that way. Here in Yolo County, the city of Davis is located on this map, and then the city of Woodland to the north. There's two main rivers here. There's Cache Creek that drains to the north of Woodland, and then there's Puda Creek that drains from Lake Berryessa just to the south of Davis. Between those two, there's a lot of flat land with nowhere to drain. There's one channel here called Willow Slough, and then other than that, there's basically just like, rural neighborhood drainage and just, ephemeral agricultural land drainage where individual landowning farmers cut channels and fill channels according to their irrigation needs. They're supposed to maintain drain channels, but there's not a lot of oversight on that. So as part of this flood-safe pilot program for YOLO, there's a plan to extend channels. Notice these black lines and then the red are levees, but there's an extension of channels that they want to do, largely around Davis and secondarily with Woodland. But the problem here basically is water can't get out. So if I go back, the water can't get off of this orange hashed area. there's a channel over here called the YOLO bypass, but the problem is that, if the bypass were to flood and you have a pipe or a channel that goes from the bypass into this floodplain area, water would just back up that pipe into the floodplain. So to prevent that, many times you'll have what's called a one-way gate or a one-way flap. And so like if you have a pipe, and on the outside of the pipe you just put a gate, and the water hits that and that keeps it closed. On the other hand, if water hits from the one side, it can open and go out, but hitting from the other side, it won't open. So there's a lot of kinds of one-way gates or one-way valves or pressure valves or whatever that can keep water on one side of a pipe and not let it into the other. And the thing is, though, once that closes, then there's no way for the water to get out anymore because the pressure is greater on the channel side than the floodplain side. Well, I have a colleague who figured out through remote sensing that something like this was happening on the Amazon River. So the Amazon, one of the largest rivers in the world, it's draining all of Brazil here, a lot of Brazil. And what you can see is a image analysis where they did remote sensing, and the blue here shows well, the sky blue, this like kind of milky blue. This is water in the channel with sediment. So water that's coming out of the mountains through the channel network is heavily sediment laden. And as a result of that, you can quickly discern it. And so then you look out on the floodplain, and there's a lot of water on the floodplain that's not sediment bearing. There are these dark blue clear water areas, and then the magenta is indicating dense flooded forest that also isn't sediment laden. Another example is a large-scale sheet wash kind of flood. So when you have a large lowland, this was from the organic flats from the wetland lecture, I mentioned this same scenario. But when Lake Okeechobee floods and this whole southern Florida Everglades area floods, then the water just passes over this whole area as one giant sheet wash. There aren't a lot of channels to carry that flow. Another type is a tributary convergence flood. So if you have many tributaries feeding to a main channel, if they all converge at the same time, then you can get a disproportionate effect. So here's a plot that shows this axis from left to right from, this is European style. So January 20th, 1995, let's see, to February 1st, 1995. So it's going from left to right. And then we're going from upstream to downstream as we go from, into the page, so to speak. And then the height here is the peak discharge. So these are hydrographs. Hydrograph is discharge through time at different cities along this river. And here, this is the Rhine River. And so you can see at this first location, there's some flow. The flow seems to linearly increase by the time you get to the next location. But then every now and then you'll see an abrupt discontinuity. Wherever there's a discontinuity, that's a location where a tributary is joining in and flooding. And some of these discontinuities are unusually large, especially like, look at this one here. So whenever, you have these multiple tributaries coming in, then they could overwhelm the capacity of the main stem river to hold that flow. And then I think this is the last one, an urban stormwater drain flood. This is a more localized context, but it's still a flood. So, in urbanized areas, we use sewers that are underground. And in fact, we put many rivers underground, as I illustrated in the urban lectures. And it just so happens that a lot of times those sewers are combined together with the wastewater sewage that's coming from our homes. So, ideally, the waste from our homes would run through independent drain lines from what rainfall is contributing. But during normal operations, normal weather, you can have a combined sewer that goes to a wastewater treatment plant. Well, the wastewater treatment plant can only handle so much inflow. And during large storms, if the inflow exceeds the treatment capacity, then the ponds fill up and then they spill and dump vast amounts of sewage into the river or whatever they're connected to. So, but in addition to spilling all the waste, you get what we call like a backwater effect. So if there's nowhere for the water to go, it's like a traffic jam for water. the water backs up in the pipes and can even back up through your house, and then the sewage could be spilling out all over neighborhoods and into your house, and it gets pretty ugly. Okay, so I'm going to stop this here, and we'll pick up again to look at the natural flow regime next.